In the second part of this presentation, I'm going to show you how to use the Stata package xtivdfreg in order to implement the IV approach that we described in part 1. This Stata package has been written by Sebastian Kripkens and myself. The latest version is available on Sebastian's website www.kripkens.de, which I highly recommend visiting because it contains several useful Stata packages, including a new subroutine spxtivdfreg, which is designed for estimating spatial dynamic panels with unobserved common factors. I will try and create another video to formally introduce this package as soon as possible. For now, I'm going to illustrate the xtivdfreg package using two examples, both of which are discussed in our Stata journal paper with Sebastian titled Instrumental Variable Estimation of Large T Panel Data Models with Common Factors. For the first illustration, we're going to make use of a panel dataset drawn from a random sample of 300 US banks, each one observed over 56 quarters. Therefore, n equals 300 and t equals 56. We're going to demonstrate two things. Firstly, we're going to show how versatile and flexible our Stata package is regarding instrumentation. And second, we're going to present an example where a regression is endogenous with respect to both error components. That is, not only with respect to the factors, but also with respect to the purely idiosyncratic error. For the second illustration, we're going to make use of the macro panel dataset of Eberhard and Thiel 2010 for estimating cross-country production functions in the manufacturing sector. The dataset contains observations on 48 developing and developed countries during the period 1970 to 2002. So in this case, n equals 48 and t equals 32. Here we will explore the capabilities of our package with unbalanced panels, given that the dataset is unbalanced. Furthermore, we're going to explore three additional features. Firstly, how to test for uncorrelatedness of covariates with respect to factors. Second, how to deal with observed factors. And finally, how to estimate heterogeneous models. The commands used in this presentation are compiled in two different separate do files and are available on my own website. Okay, so I'm going to now open my Stata. And the first thing I'd like to do is to make sure I have the latest version of the package. Therefore, I'm going to use the net install command, and I'm going to install the latest version of this package from the web. Now, as you can see, I do have the latest version, so all files are up to date and we are good to go. Next, I'm going to start with example 1, which is the banking dataset. And to start, I'm going to employ the command use, which loads into our memory a Stata format dataset from the web. In this particular case, from Sebastian's website. I'm going to increase the font. Okay, so here ID and T denote the bank and time period identifiers. ROA stands for return on assets, CAR stands for capital adequacy ratio, liquidity and size are self-explanatory, I suppose, and finally ROE stands for return on equity. In this example, I'm going to estimate the relationship between capital adequacy, bank size, asset liquidity, and profitability, proxied by the return on equity, using a dynamic panel data model. I'm going to start with the simplest possible specification for the instruments, where I use the same number of lags of all covariates as instruments. In particular, I'm going to type the command. I'm going to use a lag of the dependent variable on the right hand side, and I will also include size, return on equity, and liquidity as covariates. Now the option absorb here transforms the model in terms of deviations from individual specific and time specific means. This is in order to eliminate bank fixed effects and time effects. Essentially, what we are going to do here, we're going to allow for common factors conditional on bank fixed effects and time fixed effects. Now the option IV combines all covariates together. It specifies the same number of lags, in this example 2, and it will jointly estimate the factors that influence all of these variables for each lag separately. That is, we're going to estimate the factors for the contemporaneous value of x, for the first lag of x, and for the second lag of x. Note that by default, the package will estimate up to 4 factors, and then it will select the optimal number of factors based on the eigenvalue ratio test of Ahn and Horenstein 2013. I'm going to enlarge my command window. Now, here is the output. I'm not going to discuss the standard output in terms of estimated slope coefficients and standard errors. Instead, I'm going to focus on output that is, let's say, non-standard, that is specific to our package. So the first thing that we see here is a number of instruments reported. We use 2 lags of 3 variables in addition to the contemporaneous value of those variables. So the total number of instruments equals 9. Next, Stata reports the estimated number of factors in the covariates, followed by the estimated number of factors in U. That is, those factors that directly influence Y. At the bottom of this output, the package reports the proportion row, the proportion of variance in the total error that is due to the variance in the factor component. This statistic is very similar to what Stata reports for the xtivdfreg, fixed effects command. In this example here, we see that almost 77% of the variation in the total error is due to the single factor. Therefore, although we estimate only one factor, conditional on bank fixed effects and time fixed effects, the factor appears to be of major importance. Finally, the package reports Hansen's test of over-identifying restrictions, which is very important for model specification and instrument validity. In this example, the null hypothesis is rejected at the 5% level. As I said before, the package estimates the number of factors in X and the number of factors in U using the eigenvalue ratio test of Van and Horenstein. The default value is up to 4 factors. This could be overruled if we want to consider more than 4 factors simply by adding the option factmax, and in this case we can allow for up to 6 factors. So now Stata will estimate up to 6 factors, and it will select the optimal number of factors based on the eigenvalue ratio test statistic. Now next I'm going to make the instrument's structure more flexible by specifying a different number of lags for the covariates. So as an example, I'm gonna use this the part that is highlighted in blue will stay exactly the same, but this time I'm going to change the IV options. So I'm going to have 2 IV options. One is for size, where I'm going to specify, as an example, 1 lag, and another IV option for ROE and liquidity separately. Well, here I'm going to have 2 lags. Now notice that the factors are going to be estimated separately for size and then for ROE and liquidity jointly. So size is defactored based on the factors estimated from this variable only, whereas ROE and liquidity are defactored separately based on factors estimated from these 2 variables only. Note that the total number of instruments this time equals 8. This is because we used 1 lag less for size. It is also possible to set the number of factors extracted from each set of instruments equal to a pre-specified value. For instance, if we wish to impose estimating 2 factors for size, I'm going to add 2 sub-options, factmax 2 and also no eig ratio. So here, within the first sub-option, we set the maximum number of factors equal to 2, and with the second sub-option we instruct our algorithm not to use the eigenvalue ratio test. So we impose 2 factors in size. Note that once we do that, we end up with an asterisk in the reported number of factors in X. This is because we end up having a different number of factors for the covariates, that is 2 factors for size, and then we end up estimating 1 factor for the remaining variables. So if the estimated number of factors differs for the covariates, we get an extra output at the very bottom, where Stata reports the actual number of factors for each of the X's. So 2 factors for size, and which we have imposed, and 1 factor for the remaining covariates that we have estimated. The ability to specify the number of factors a priori can actually be really handy when we wish to avoid defactoring certain covariates. Suppose, for example, that one covariate is independent from the factors that influence y. In that case, this particular covariate can serve as an instrument for itself. That is, no defactoring is actually required. To achieve that, I'm going to run exactly the same command, except I'm going to set the maximum number of factors equal to 0. And of course, in that case, we don't really need to invoke to the no-ig ratio suboption because the minimum and maximum number of factors is 0. I will show you how to actually how useful this suboption is when we test for uncorrelatedness of certain covariates with respect to the factor component. But for now we see that again we get an asterisk here, we impose no factors in size, so size is used as an instrument for itself, and one factor is estimated jointly from ROE and liquidity. Another possibility here is to estimate the factors based on a subset of the covariates, and then defactor all variables based on those factors alone. Now, to achieve this, we're going to add the sub-option phi var. So let me now call the initial command. This is what we estimated initially, but in addition I'm going to add the phi var option So here we have combined again for simplicity all variables together. We specify two lags. However, the factors are estimated jointly based only on these two variables. This sub-option could be useful, for example, when the x's are measured in very different units. Now, to this end, we can also standardize the variables within the IV option before the factors are extracted. To achieve this, I'm going to go back to here, the previous command, and add the sub-option std. So what this sub-option is going to do is it's going to standardize these variables so that they have mean 0 and variance 1, and then it will extract the factors based on those standardized variables. I would not really recommend this option unless it is absolutely necessary. Okay, now, as we discussed in the main presentation, one important case that may often occur in empirical circumstances is endogeneity. So as an example of dealing with endogeneity, suppose that ROE suffers from reverse causality. That is, not only ROE causes CAR, but vice versa as well. Suppose also, as an example, that a different measure of profitability can serve as a valid instrument. That is, suppose that the return on assets is exogenous with respect to the purely idiosyncratic error, although it may still be correlated with the factors. In that case, I'm going to rerun the initial command, but replace ROE for ROA. So this is an external variable that is used to instrument the variable that is endogenous with respect to the idiosyncratic error. It's as simple as that. Now bear in mind again that all these specifications are used for the purpose of providing examples and for the purpose of illustration, so there is no point in trying to justify whether ROA is actually exogenous or not when a difference proxy of profitability is not. Now I hope this exposition has been able to showcase some of the capabilities of our package, at least when it comes to instrumentation. Next, I would like to consider a different example using the macro panel dataset of Eberhard and Thiel 2010 for estimating cross-country production functions in the manufacturing sector. The dataset is unbalanced, so here we're going to explore our package with unbalanced panels and explore also three additional features. First, how to test for uncorrelatedness of covariates with respect to the common factors. Second, how to deal with observed factors. And thirdly, how to estimate heterogeneous models. As before, I'm going to load the dataset into the memory temporarily. So here is the dataset. Again, let me increase the font a little bit. Okay, so ID and T denote the country and time period identifiers. Sorry, that is list and year. Yeah, list and year denote the country and time period identifiers. LY stands for logged output, and L capital L and LK denote logged labor and logged capital respectively. So let's start with a basic model where no logs of output are included on the right hand side. So we estimate a static panel, and moreover we use the same number of lags of labor and capital as instruments. So in this specific case, 3 lags. The default number of maximum allowed factors is 4. We can overrule that by playing around with the sub-option factmax. Oops. Notice here that since the dataset is unbalanced, our package employs a variant of the expectation maximization approach in order to estimate the factors. This approach has been proposed by Stock and Watson 1998 and by Liao and Yang 2015. It is an iterative procedure, the details of which are documented in our Stata journal paper. So here every dot in this output represents a different iteration step. There are 5 dotted lines reported here. The first line of dots reports the number of iterations required to estimate the factors jointly in the contemporaneous values of labor and capital. On the other hand, the second, third, and fourth lines of dots report the number of iterations required to estimate the number of factors in the lagged, second lagged, and third lagged values of labor and capital jointly. Finally, the last line corresponds to factor estimation from the first stage residuals, which is relevant for the two-stage IV estimator. The total number of iterations for each estimation appears here. So as we can see, in all cases up to 6 iterations turns out to be sufficient for convergence. Now next, suppose we wish to test whether capital is uncorrelated with the factors that directly influence output, or test whether capital is not subject to a factor structure at all. Now, the robust estimator is going to treat capital as correlated with the factors, and therefore it will de facto this variable as per usual. Now, although robust, this estimator is not going to be efficient under the null, because in that case there is no really need to de facto capital. So I'm gonna estimate this estimator and store the estimates with the name two-stage IV robust. Now the efficient and consistent under the null hypothesis estimator is the one that uses capital as an instrument for itself without the factoring. That is, for this specific variable, we're going to impose 0 factors. So I'm gonna enter that, and finally, in Stata, we can conduct a Hausmann test in this way here. So the first estimator is a robust. The second estimator is the one that is efficient under the null, but inconsistent under the alternative. In this specific case, the null hypothesis is rejected at the 5% level of significance, meaning that the null hypothesis of exogeneity of capital with respect to the factor component is not supported by the data. In what follows, I'm going to show you how to deal with observed factors in our model. So suppose that the model contains observed factors, common influences that we can actually observe, but we also wish to be able to control for unobserved factors as well. Now, for the purposes of illustration, I'm going to generate a linear trend as an example of an observed factor. Indeed, if we plot the dependent variable logged output for up to the first 12 countries, we can see that adding a linear trend is not actually implausible. It's not a bad idea. Yeah, here it is. So there is a small positive trend which we can actually add. We can treat that as an observed factor. So to do that, I'm going to generate the trend based on the year variable. So the year is a variable that goes from 1970 up to 2022. So I'm going to generate the trend. And now what I'm going to do is I'm going to rerun the same command as before, except I'm going to include trend as a regressor, and then I'm going to use trend as an instrument. Therefore, I will impose that trend is not defactored. So I'm going to impose 0 number of factors and 0 lags as well. So I'm just going to use the contemporaneous value of trend as an instrument for trend itself. Notice here that in the absorb option, I do not include the ID or the list, the country identifier, sorry, the year identifier, the period identifier, because it does not make sense to add time dummies while trying to estimate the impact of variables that are common across individual units. Again, we get an asterisk for the number of factors in X. We estimate one factor for labor and capital, and we impose no factors for trend. So this is an example where actually imposing a pre-specified number of factors a priori becomes really handy. Now the last thing I'd like to demonstrate here is how to estimate a heterogeneous model. To this end, I'm going to add, so this is pretty much the same command as before, and the only thing I'm adding extra is this option mg. Note that there is no result reported for the over-identifying restrictions test because Hansen's statistic is applicable only to the pooled model. So this is the mean group estimate of logged labor and the mean group estimate of logged capital. If we wish, we can actually report estimates for a specific country alone. I can achieve this by adding to this mg option brackets has, where this is the number corresponding to the country I want to report. So for example, the first country equals Australia. So if I add brackets 1 here, I'm going to get the first stage IV estimate for Australia. It is actually possible to save all country-specific coefficients in a table. So let me show you how to do this. So I'm going to run the mg estimator again, and then I can extract the slope coefficients which are stored in these metrics here. I call this matrix beta I, and I'm going to list these metrics. So the first column denotes the country-specific estimates for the logged of labor. The second column reports the country-specific estimates for logged capital, and these are the individual specific intercepts. We can also extract the corresponding standard errors by generating a new matrix. I'm going to call this SC_I, and these are the standard errors for the country-specific IV regression. So that is pretty handy. You can of course copy and paste this output into Excel for further analysis. As a final remark, note that if we wish to estimate the impact of an observed factor for the mean group estimator, like trend, we should avoid double defactoring for this specific variable. Here. So normally for the mean group estimator, we conduct double defactoring in a single stage. If we do have an observed factor, we should avoid double defactoring this specific variable. The reason is that double defactoring is going to eliminate the observed factor from the model, rendering identification impossible. In order to avoid double defactoring for trend specifically, we can go back to the output and now add the sub option no double defact. So if we click this, you can see now that we impose no factors, 0 factors for trend, and in the double defactoring operation, we only use labor and capital. Now, before I finish, I would like to make a couple of remarks. First of all, it is not absolutely necessary to eliminate individual fixed effects using the absorbed option. For example, we can eliminate fixed effects using first differencing. Let me show you how to do that. So I'm going to use essentially the first difference operator that is available in Stata. And then I'm going to add the model covariates in differences. I'm going to specify as an example 3 lags and also the option no cons. Okay, so here we have eliminated individual fixed effects using first differencing, and then we have proceeded as usual. On a different note, in the absence of any defactoring at both stages, xtivdfreg reduces to the popular xtivfreg package. Now our package becomes handy here because unlike the standard xtivfreg command, here we can allow for slope parameter heterogeneity when the option mg is invoked. The help file of our Stata provides an example that demonstrates the equivalence between the two estimators here, and therefore I will refer you to that. And that's it. So I hope you have enjoyed the session. I also hope that my presentation has been clear enough in terms of demonstrating the capabilities of our package. In the near future, I'm going to try and create more videos illustrating other Stata commands I've written with co-authors. If you are interested, feel free to visit my website, follow me on LinkedIn or Twitter, or subscribe to my YouTube channel. Thank you so much, and good luck to your own research.